this video, we're going to look at a couple more examples of these 3 by 3 systems. So in this system here, we again have three equations, which I'm going to label as equations 1, 2, and 3. And just like we did in the previous video, our goal with a 3 by 3 system is to take these three equations, separate them into two pairs, and then eliminate the same variable from both pairs in order to create a 2 by 2 system. Now, when we're deciding how to pair our equations together, there is no wrong way to pair them. No matter how you do it, no matter what variable you eliminate, as long as you're consistent and all your math is right, then you will get the right answer no matter how you do your pairs. But that doesn't mean that there isn't necessarily an easier choice or a harder choice. So when I'm looking at this, I like to think about if there's any variable that looks like it might be easier to eliminate, if there's less work involved in eliminating it. And what I notice is that in equation 1, we have a negative y, and in equation 3, we have a positive y. That's going to be an easy variable to eliminate because they're already exact opposites of one another. All right, so let's go ahead and create these pairs. So I'm going to put equation 1 with equation 3. Okay. Now, for our other pair, we need to make sure that we eliminate the same variable. So we can either pair together now equations 1 and 2, or we could pair together equations 2 and 3. Doesn't matter which way you go, you're going to end up with the same answer, but again, try and see if one of them maybe looks easier. So to me, with equations 2 and 3, it looks just a tad bit easier maybe, because we already have the negative and the positive, so they're already at least opposite signs of one another. So it'll be one less thing that we have to worry about when we're trying to eliminate that variable. So that's going to be my choice, is putting equations 2 and 3 together. Okay. All right, so now we can start eliminating. All right, so in our first pair over here, the whole point of putting 1 and 3 together was that the y's just eliminate right off the bat, so that's easy. And then if we add these two equations together, we'll end up with 6x minus z is equal to 8. Okay, I'm going to go ahead and call that my equation A. All right, so we're going to leave that for a second. We're going to go over to our second pair with 2 and 3. Now this time we have to do a little bit more work in order to eliminate the y variable, but it's still going to be pretty easy. So remember, since we eliminated y in our first pair, we have to eliminate y in the second pair as well. It's important that you're always eliminating the same variable from both pairs. If you eliminate a different variable, you're not going to get anywhere. It's not going to help you with anything. So the easiest way to eliminate y on this one would just be to multiply that bottom equation through by 3, because that would give us a positive 3y and a negative 3y, which are opposites of each other, times 3. All right, go ahead and rewrite your system. So 2x minus 3y plus 4z is negative 15. That's still the same. We haven't done anything to equation 2. And then equation 3, we're multiplying the whole thing through by a positive 3. So we would get 15x plus 3y minus 6z is equal to 36. And then go ahead and add your equations up. So the y's cancel. That was our whole point. And then just add the rest of it. So we'd get a 17x minus 2z is equal to 21. And that is what I'm going to call equation B. Okay, so now we have our 2 by 2 system. So putting together our equations A and B, A and B together, we now have a 2 by 2 system. So now we just keep going with it, okay? At this point, if you prefer to switch over to substitution, you can. I like to just stick with elimination usually because then we're just doing the same thing the whole way through, and it's a little bit easier in my opinion to just kind of autopilot your way through it. It's a little bit easier to think about. So I'm going to carry on with elimination. And again, doesn't matter which variable you eliminate, but if one of them looks easier, go that route. So definitely on this one, the z's are going to be easier to eliminate. So with the negative 2z on the bottom, if we had a positive 2z on the top, we could eliminate those. So we just need to multiply that top equation through by a negative 2, since it's already negative. The double negative will give us the positive that we need. All right, rewrite our system. So multiplying equation A through by a negative 2, all right, we would get negative 12x plus 2z is equal to negative 16. And then bottom equation, I'm just going to copy right over. All right, and then just add them up. So adding these together, our z's cancel, and we would get 5x is equal to 5, which just dividing by 5 on both sides, we end up with x is equal to 1. So that is our first variable. All right, once we find the first variable, it's just back substitution from here. So the first step of back substituting is to go back to either equation A or B, plug in our x equals 1, and solve for z. So equation A looks a little bit easier to me, smaller numbers to work with. So we'll have 6 times 1 minus z is equal to 8. And just solving that out, we get 6 minus 8 is equal to z, or z is equal to negative 2. All right, and then once you have two variables, go back to one of your original 3 equations, either 1, 2, or 3, plug in the x and the z, and solve for y. Again, you can pick any of the 3 equations. That's the beauty about systems, is you're finding a solution that works for all 3 equations, but pick the one that looks easiest. So equation 1 definitely looks the easiest, smallest numbers to work with. So I'm just going to plug this back into equation 1. So we'll have x minus y plus z is equal to negative 4, just plugging in 1 for x and negative 2 for z. So that would be negative 1 minus y equals negative 4, or negative 1 plus 4 is equal to y, which means y is equal to 3. All right, and then just putting our variables together, just x, y, z, we'll have 1, 3, negative 2 as our final answer. There you go. All right, so there are lots of examples in the notes that I posted up on Blackboard, but I am going to jump to number 7. And if you guys want to see any more of these, systems worked out, just send me an email and let me know, and I'd be happy to make videos for more of them. The last one I'm going to do in this video is number 7, just because it's a little bit different. I want you to see some variety. Okay, so looking at this system in number 7, something should jump out at you here, and that's that our top equation only has 2 variables in it. It only has the x and the z. Now, believe it or not, this is actually going to make our lives a little bit easier. So normally when we're dealing with a 3x3 system, we take our 3 equations, we split them up into 2 pairs, and then we eliminate one of our variables. This time though, because our top equation already only has 2 variables in it, we don't have to do anything to equation 1. All we have to do is take equations 2 and 3, eliminate the y variable that's missing from equation 1, and we'll have our 2x2 system. So let's go ahead and see how this works. All right, so I'm going to put together equations 2 and 3. These are the ones that actually have all 3 variables in them. So that's my equation 2 and 3. Okay, now the main difference here is that because that top equation only has 2 variables in it, we don't have choices this time like we typically do. The only variable that we can eliminate is y. Typically, you get to choose whether you want to eliminate x, y, or z, but this time we don't have a choice. Because that top equation is missing the y, we have to eliminate the y variable. So that's going to be pretty easy. Our equations right now, we have a negative 2y and a negative 2y, so we're almost ready to eliminate. Just remember that we need these to have opposite signs of each other. So we just need to multiply one of these equations through by a negative 1. I'll go ahead and just do the top equation. So multiplying that top equation through by a negative 1, we would get negative 4x plus 2y minus z is equal to negative 7. And then just copy that other equation over. And then add these up. All right, so adding these together, our y's cancel. That's how we designed it to happen. And then we'll get a negative 2x minus 8z is equal to negative 26. I'm hoping to finish this video before my battery dies on my iPad. Okay, so now I'm going to call this equation A. All right, so with this system then, instead of having to go through another pair to find an equation B, what we're going to do is put together our equation 1 with our equation A, and that is going to be our 2x2 system. So x plus 4z equals 13, and negative 2x minus 8z is equal to negative 26. That's the equation 1 with equation A. All right, so now let's just continue with our elimination. And you could, again, switch over to substitution here if you prefer. That's up to you. All right, so I'm going to go ahead and try and eliminate my x variable. So since we have a negative 2x in the bottom equation, easiest way to eliminate that would be to multiply the top equation through by a positive 2. So then this system would turn into 2x plus 8z is equal to 26 is our top equation. And then the bottom equation is just the same. All right, and then add those 2 equations up. And you'll notice the x's cancel because we have a positive 2x and a negative 2x. But the z's also cancel because we have a positive 8z and a negative 8z. And the constants also cancel because we have a positive 26 and a negative 26. So everything is going to cancel out here, leaving us with 0 equals 0. Well, because all of our variables canceled out and we're left with a true statement, right? 0 does in fact equal 0. This is our case of infinitely many solutions. And remember we discussed before that if all your variables cancel out and you have the same number on both sides, that's when it's infinitely many solutions. But if you had a different number on both sides, that would be a false statement, so it would be no solution. In this case, of course, though, it's the same number, so it's infinitely many. All right, guys, so there are more examples posted in the notes on Blackboard, so look through them, and if you want to see any more of the examples worked out in videos, just send me an email, and I would be happy to make a few more.